Hi everyone, Mrs. Hanson coming back with Chapter 4. I hope to be the last lesson with our last topic on cycloalkanes, Section 4.9 to the end. So as we look at an example of a cycloalkane, for example, a cyclopropane molecule. With a cyclopropane, you can see that there are 3 carbons in a cyclic structure. 3 carbons in making an equilateral triangle, you could see that there would be a 60-degree bond angle. If indeed a cyclobutane laid flat on the table, cyclobutane would have a 90-degree bond angle like a right edge. Here you can see if cyclopentane laid flat on the page, it would have a 108-degree bond angle. Cyclohexane, a hexagon there, 120. Here is cycloheptane, cyclooctane, and we start to see variants for that sp3 hybridized carbon. Now remember the tetrahedral shape of sp3, every carbon having 4 bonds, the ideal bond angle was 109.5. So if cycloalkanes were indeed flat, each carbon in the ring would experience significant angle strain. And keep in mind that, when we build these molecules, we're often fooled into thinking they're flat on the paper, but they're not. Just as the zigzag line represents the carbon chain that we call a straight chain, we understand that the zigzag line is really representing a more accurate depiction of the carbon chain, knowing that you have 109.5 degree bond angles. So what we're looking at is kind of expanding the bond angle by adding more and more carbon into the cyclic structure and kind of challenging ourselves to start thinking in these, in a 3-dimensional cyclic structure where they're going in zigzag lines as well, up, down, even if they're though in a cyclic structure. So when we analyze cycloalkanes, we analyze the bond energy through a combustion experiment. We gather the amount of energy from combusting that it's a type of fuel, the cycloalkane, and how much energy was required to break bonds is then measured. It actually shows that the 6-membered ring, the cyclohexane, has the lowest heat of combustion per CH2 group. And what that means is that it would have the lowest energy in its 3-dimensional position. It is the most stable conformation for a cyclic structure. So we spend a lot of time talking about cyclohexanes in organic chemistry simply because a 6-membered ring is the most prevalent type of cyclic structure simply because it exhibits the least amount of ring strain, it is of lowest energy, and therefore favored in nature. Close to that would be a cyclopentane, a 5-membered ring, close to that, very close really, 658. And it's really 657 is cycloheptane. So a 5, 6, 7-membered ring are favored in nature, 6-membered rings being the most stable. Cyclobutane, for example, is 27 kilojoules per mole less stable than cyclohexane for each unit of carbon. The angle strain, here's that 4-membered ring, cyclobutane, which a moment ago I said, remember how we're tempted to think of cyclobutane looking like a flat square on a paper and we might think it's 90 degrees, but it's puckered. If you would actually grab your molecular model kit and put 4 carbons into a cyclic structure, you start to see that it creates a puckered type of conformation. Carbons, we'll call this, how about 1, 2, 3, 4. Carbon 1 and 3 kind of are in the same plane. Carbon kind of looking down here, those are kind of going down from the paper. So we call that kind of a puckered conformation. So again, very much of a strain. We call it a torsional strain with non-ideal bond angles. Cyclopentane, we realized, is a little better because the angle strain has been alleviated. The bond angles are very near the desired 109.5. And you can still see that it has a flat area up here and then a puckered region where all 5 carbons. But I can clearly see that these bonds are giving more space for the hydrogens, so there's very little interactions between the hydrogens for steric hindrance. And we actually have what we refer to as an envelope conformation, and that alleviates the angle strain. But cyclohexane, as we mentioned, is indeed the most stable arrangement for a cyclic structure, 6-membered carbon ring. Both cyclopentane and cyclohexane have very close 109.5 degree bond angles, but we alleviate a little of that torsional stress, a little bit of the steric hindrance with the 6-membered cyclic structure. We have 2 really important conformations of cyclohexane. We'll learn to call the chair conformation and then the boat conformation. We see that there are many conformations for cyclohexane, but it's the chair and the boat conformations that we'll look at first. So a 6-membered ring, and each carbon will have 2 hydrogens coming off of it. So remember, on a piece of paper, if you were to draw cyclohexane, each carbon, of course, has 2 additional hydrogen bonds coming off, right, to complete the 4 valence requirement for a carbon atom. And so how do we arrange those 6 carbons so that they're alleviating any steric hindrance, any torsional strain for the carbon-to-carbon bond? And the most stable conformation is in a chair position, and that's what this represents. Carbon to carbon, up, down, just like you would draw, in a zigzag line for a straight chain, how we went up, down, up, down. The same is true even if it's a cyclic structure. Carbon 1 leads down to carbon 2, which leads up to carbon 3, which leads down to carbon 4, up, down, up. We're looking at no torsional strain with that type of configuration. And this is what we refer to as the chair conformation. I'm not sure why, if this is considered like a little headrest and a little footstool, and you can maybe perhaps envisioning someone sitting in a chair, but that's what it's called. It's called a chair conformation. Then if you were to take the end carbons, so if let's call this carbon 4 and this carbon 1, and you flipped carbon 1 up and left carbon 4 up as well, you get the boat conformation. Carbon 1 and carbon 4 both tilted up. And so you see the little boat here. This kind of gives rise to, I don't know, a little person sitting in a boat here, and this would be the ends of the boat pointing up. Or you could flip it over and the boat would be pointing down. But that's how we've named them, the chair and the boat conformation. And clearly you see these are not equivalent. In this chair conformation, we said, look at all of these hydrogens with these nice 60-degree separation between the front and the back carbons, lots of room, so no steric hindrance, no torsional strain. And yet in this boat conformation, carbon 1 and carbon 4, if they're placing their carbons up in the same direction, notice that the hydrogens are going to have interactions, and that of course creates strain. We have an eclipsed hydrogen to hydrogen steric hindrance. These are going to be called flagpole interactions. We'll learn in a little while about axial and equatorial bonds. Those axial bonds act as flagpoles. They're just sticking straight up in the air from the carbons. Look at all the possible conformations for cyclohexane. We saw the most stable of lowest energy as the chair conformation, and its mirror image over here, the chair conformation. If you were to take this carbon and kind of flip it up, leave this side the same, but flip up this carbon, you get a half chair. That's the least stable conformation. And if you twist carbon 1 and carbon 4 a little bit, you get a twisted boat, back to the twisted boat, back up to the half chair, and finally the chair conformation. So since the chair conformation is the most stable because it has the least steric hindrance, it has no interactions from position 1.4. From there, this is where we'll focus our studies, the chair conformation. So this chair conformation with its no angle strain, no torsional strain, and all the adjacent carbon to hydrogen bonds are staggered. So if you look between this carbon and this carbon, you can clearly see all of the arrangements here are in the staggered position, meaning that there's no hindrance, no interactions between hydrogens and hydrogens as we twist and look down those molecules. So all other conformations have some sort of ring strain, some sort of torsional strain, some sort of steric hindrance that's interacting. And so because the chair conformation is the most stable, it's the one that we most commonly draw and discuss about, in terms of chemistry and thinking about how a cycloproduct will form. So one of the first skills we have to practice is learning how to draw the chair conformation. Draw the chair conformation, and that literally is one of your homework questions. It says do this so many times that you figure out how to draw a cyclic structure with 6 carbons and ends up looking like a chair, the most stable conformation. This is your book, Draw a Wide V, and you can see this is kind of a wide V, and you think about left and right side of that. And your second step says draw a line going down at 60 degrees. So approximately here would be your next step. And then just ending before the V hits the center, right? So I'm not going to go too far. Draw a parallel line to this line up here, step 3. Come back down and then join them together, connecting the dots. You will know as you go through how to draw these, it just looks correct because there will be 3 sets of parallel lines by the time you're done drawing. So let's kind of emphasize. These 2 lines are parallel. See how they're in the same direction. These 2 lines are parallel. They're in the same direction. And these 2 lines are parallel. That's the goal of drawing a chair conformation of cyclohexane, drawing 3 sets of parallel lines. I don't know about you, but it takes practice for me to get that down, and I still am not perfect at it, especially if I'm going fast. 3 sets of parallel lines. So this is my trick. This is what I do. I start by drawing 2 sets of parallel lines. That's my first step. And I know now they're parallel. I need 3 sets of parallel lines, so there's my first 2. And then I'm going to take a dot and I'm going to draw it just left of the center and then over here just right of the center. See, I'm kind of drawing 2 dots. Not quite down the center, but left and right. Then I can simply connect the dots and I end up with a pretty okay cyclohexane structure. It's never going to be perfect, especially when I'm drawing fast. Now keep in mind this has a mirror image as well. So if I start in the other direction, start your parallel lines kind of tilting the other way, draw your 2 dots in the center, again just left and right of that imaginary center line between those 2 parallel lines you started with. And you can see then you can connect the dots and end up with a reasonable structure that represents 3 sets of parallel lines. The faster I go, the more sloppy it looks. I really do have to take my time. And the other thing I would encourage you to do is to build a cyclohexane using your molecular model kits and really understand the conformations. What does a boat look like? How do I push this, this carbon up to end up with a boat conformation? And then really spend some time with the hydrogens. I encourage you to add all 12 hydrogens to the cyclohexane and really get an idea about the axial and equatorial positions. And let's talk about that. Every one of the carbons will have an axial and an equatorial position. Let's suppose I called this carbon 1. Carbon 1 would have a bond pointing straight up out of the page right here, just straight up. That's what I call a flagpole. Just like a flagpole comes out of the ground rising straight up. Flagpoles are known as axial positions. The other type of bond that every carbon will have is called an equatorial bond. Think of the term equator. And if you have a circle, kind of like the cyclohexane structure, the equatorial bonds are around the center, just like the equator goes around the Earth. So their equatorial are tucked around the center, and axials come up or straight down from the structure. So at this slide, we're just defining the terms. If it's coming straight up or straight down from that carbon, those are known as axial. If they're going around the center of the structure, those are known as equatorial. Every carbon has an axial and equatorial bond. Very critical to see that. Let's also figure out where we find the axial and equatorial bonds. If I labeled this carbon 1 and just denoted that its axis is going straight up at carbon 1, that's the axial bond at carbon 1, carbon 2's axial bond must point straight down. Carbon 3 will point straight up. Carbon 4 will point straight down. 5 is up, 6 is down. Do you see how they alternate as you go around the ring? Carbon 1 was up, carbon 2 down, carbon 3 up, carbon 4 down, carbon 5 up, carbon 6 down. So axials will alternate up-down positions. Now, the same is true for the equatorials. They are going to alternate up-down as well. Not coming straight, but kind of encircling like an equator. Now remember, carbon 1 is what I called this guy, and we said carbon 1 points straight up. That's its axial bond. That means if the axial is up, the equatorial must point down. Not like a flagpole, but circling the equator. That's pointing down. Carbon 2 had a flagpole, the axial pointing straight down. So the equatorial must point up, not like a flagpole, but around the circle. Carbon 3, axial was up, so equatorial was down. Carbon 4, flagpole was down, so equatorial is up. Carbon 5, axial was up, so equatorial was down. Axial down, equatorial up. They always alternate as you go up, down, and encircle the ring. That's true for the axial and the equatorial. And friends, this is so critical to see. Take your time and envision this with your molecular model kit. When we look at a monosubstituted cyclohexane, one substituent coming off of a carbon, we have a couple of ways to actually represent that. We could represent that substituent in an axial bond, or we could represent that in an equatorial bond. They are exactly the same structure. The ring has just flipped from one conformation to the other. So when I say flip, I want you to envision this is carbon 1. I know it is because it has the branch coming off. I'm going to say it's a halogen, just the element X. And I want you to flip this carbon, still number 1, flip it down and force this carbon to go up. I'm not suggesting you just twirl it in space. I want you to physically push down this carbon so it's forced down. And you'll see that this then is forced up to keep the chair position. Notice how now our set of parallel lines has switched. The parallel lines that we drew originally were parallel in this direction, but in a ring flip, they're now going in the opposite direction. What was carbon 1 up high has been pushed down. Here's the location now of carbon 1. We pushed it down, forcing carbon 4 up. 1, 2, 3, 4. A ring flip. Carbon 4 was pushed down. We took our hands and we literally forced it up. At the same time, we pushed carbon 1 down. We're flipping the ring. Not spinning it in space, but flipping it by pushing on carbon bonds. Notice this critical junction here. I want to just clean this up and stress. Carbon 1 had an axial bond pointing up. This is still carbon 1. The bond is still pointing up, but it's now equatorial. Axial up. When I do a ring flip, it stays up, but the position has gone from axial to equatorial. That's what happens with a ring flip. So this ring flipping occurs by rotation of all the carbon-to-carbon single bonds in the ring. Axial substituents become equatorial, and equatorial become axial, and the number of carbons kind of just flip from up to bottom, up to down. But I want to stress, if something was pointing up as an axial, it will still be pointing up. It's just now in the equatorial position. Let's take some practice there. Oh, I should spell right. Let's draw both chair conformations of bromocyclohexane. So I'm looking at bromocyclohexane. What would that look like in a three-dimensional chair structure? We'll just begin by drawing the first chair conformation and place bromine in any position. So the way I've learned to draw cyclohexane, I just draw two parallel lines at a slant. I connect, kind of put two dots in the center off. I don't draw them right on the center between the two. I draw them off center, and then I just kind of connect the lines. And I come up usually fairly okay. And now it's just saying select a spot to put bromine. There is absolutely no wrong. You have 12 positions. 12 because here's 1, 2, 3, 4, and so forth. There's 12 positions by the time I'm done selecting. So let's make it just a little bit different. I'm going to put, let's put bromine facing down here. I'm going to say this is down. It becomes carbon 1. It's down in an axial position, meaning this was equatorial. Now, perform a ring flip. When I say a ring flip, take carbon 1 and push it up, take carbon 4 and push it down. You're twisting all 6 carbons in their single bonds. You're twisting them to change shape. Now here's how I draw that. Notice how I had my parallel lines going in this slanted direction originally. So now I'm going to slant them in this direction. So I'm just taking the opposite approach. I draw my 2 dots in the center, and that's not going to be perfect. So I'll come up with, let me try that better. I can already tell it's going to be off. So when I connect now, I get something that looks like this. Whoops. Close enough. So what was carbon 1 is now up. Here's carbon 2, 3, 4, 5, 6. Carbon 4 was up, it's now down. See that? So carbon 1 had a down axial. That means it's going to have a down equatorial bromine. It still stays in the position pointing down, but now the axial has turned into the equatorial bond. So we just did a chair flip. Not too shabby. Oh, there's a slew of these for you to do. Draw both chair conformations. So I think the easiest thing for me to do is to begin by practicing drawing the darn chair best you can. How's that look? So just to repeat what I'm doing, I draw 2 sets of parallel lines, and I kind of just put 2 dots in the center to help me, locate where I'm going to attach, and then usually it comes out okay. That's close enough. Just pick anywhere to put the OH. There are so many correct choices. And when you draw the chair flip, just simply draw in the opposite directions for your parallel lines. I still need my two helpful dots there to connect. I know they sometimes end up looking like bow ties, and that's not perfect, but it's the best I can do. If this is carbon 1 was pushed down, carbon 4 was pushed up. So now here's carbon 1, here's carbon 4. All right, just to let you know where they ended up. Carbon 1 had the axial pointing up. So the equatorial, which has a hydrogen, was pointing down. So now, if the axial was pointing up, it will be an equatorial pointing up, and the hydrogen is then pointing down on an axial. We did a ring flip. Oh, let's try another one. Let's try this amine group. That's as good as I get. I hope yours look better, but don't feel bad if they don't. You want to try it up here? Oh, just to mix and mingle a little bit. So again, if I place it on an axial, I don't know, should we try something? What if this is equatorial down? I mean, there's no wrong. I'm just trying to find something different. Let's say it's equatorial pointing down. Do a ring flip. So this carbon 1 gets pushed down, carbon 4 gets pushed up. And all that means is just start with your lines tilted the other direction. Connect my dots. Carbon 1 now is down here. The equatorial becomes an axial, and the amine group becomes an axial, still pointing down. Oh, I can't stress enough how fun it is to draw cyclohexanes. When we consider methyl cyclohexane, the chair conformation where the methyl group is in the equatorial position is the more preferred conformation, the more stable conformation, simply because we have less steric hindrance. Remember that we might not see it, but up here at position 3, let's call this carbon 1, carbon 2, carbon 3. Even though they're not drawn, we know that there's hydrogens there, and hydrogens take space. And even though this isn't drawn, we know it's there. There's a hydrogen there. So you have kind of this axial steric hindrance when I have this methyl group pointing straight up off of a flagpole. This takes space, and those are going to be talking to each other. Whereas in the equatorial position, it's kind of tucked around the sides of the molecule, right? There's no flagpole standing straight up, either straight up or straight down, but it's tucked in kind of away from all of the axial bonds, and that's less steric interactions. So the axial position causes steric interactions and destabilizes that cyclic structure. And that's kind of what I was trying to draw. If this is our methyl group, see how large of that space that it's occupying? I'll call that carbon 1. And as I travel in both directions, these are known as the third position from carbon 1. And you can see that you have some interactions, some diaxial interactions, which cause gauche interactions, steric hindrance. And clearly I see if I had tucked the methyl in the equatorial position instead of the axial position, there are no gauche interactions. There are no 1,3 diaxial interactions. That's saying the same thing. It's just in a better spot away from other people's electron clouds, if you will, and thus a more stable configuration. Now, notice this trend. If we examine this chart, larger and larger substituent groups cause more and more steric crowding in the axial position. So if I have a somewhat small substituent like a chlorine, and I think about what I've just said as I draw that structure, if I put a chlorine in the axial position versus a chlorine in the equatorial position, oh, that is not good. That's kind of putting it here. Roughly, you have about 70-30, the axial equatorial ratio. So I'm not looking at a terrible amount of hindrance because this is a pretty tiny substituent branch. But as the substituent branch gets larger and larger and larger, and oh my gosh, look at this big bulky branch. It's called T-butoxide. That would be like taking this cyclic structure and putting a carbon that's leading off to 3 other carbons. This carbon is attached to 3 other methyls, 1, 2, 3. That is a big, bulky group. And that big, bulky group creates all kinds of steric hindrance in the axial position. So you would not find it standing up on the flagpole. Instead, you would see it tucked here along the equatorial position where it's out of the way. Alrighty, so definitely prefers the equatorial ratio over the axial. The bigger and bigger and bigger the molecule, the branch becomes, the greater the steric hindrance. I selected this question from your homework because it was a thinker. And it says the most stable conformation of 5-hydroxy 1,3 dioxane. So, all right, what it's looking at is there's a hydroxy group here. See this OH? And a 1,3 dioxane. That's just telling us that there's ether linkages in here in that particular structure. So I have this up in the flagpole position. Notice that this OH is truly in the flagpole or the axial position, and it's saying that's the most stable conformation over the equatorial. That if I were to try to draw this molecule, best I can, leading this position, and I were to draw this in the equatorial position, this is less stable, and they're asking you to consider why. And it makes us think back to our first chapter when we reminded ourselves about intermolecular attractions. Notice what this molecule can do, very special, is set up intermolecular attractions, meaning within the same molecule. The hydrogen here on the hydroxyl group can set up very strong hydrogen bonds, which helps to stabilize that molecule. But see how specialized that is? This OH talking and communicating to the oxygens as part of the cyclic structure, creating hydrogen bonding. It's such a rarity, it ended up kind of as a think about this question in your homework. Whereas the vast majority of any type of substituent branch is going to prefer the equatorial position. Well, let's consider what type of interactions occur with disubstituted cyclohexanes. With multiple substituents, we have to rely on solid or dashed wedges to indicate which position is going to be favored. Is it pointing up or pointing down? And notice that if you see a wedge, we call that pointing up. And if you see it represented as a dash, you'll see it pointing down. And you're going to be asked to go from this cyclic structure into the chair conformation and be able to draw the accurate configuration. So again, with our cyclic structure, I can choose to just draw my parallel lines and create the cyclic hexane. If the chlorine is on carbon 1, and it just does so by alphabet, we're just alphabetizing those numbers. I'm sorry, we're going to alphabetize the letters. We don't alphabetize numbers. 1-chloro, 2-methyl cyclohexane. So in the chair conformation, let's call this carbon 1. Chlorine needs to point up so I'm going to make that an axial position. Right next door to it is carbon 2. It must point down because it's the dashed position. To point down, carbon 2 must be an axial position. Now you could have made them both equatorial. That doesn't matter. It's the chlorine has to be up and the methyl group has to be down. So emphasize what that means to you. If you start to think about drawing, what would it have done if both of these were dashes? So think about what that does to the structure. If both are dashes, they're both going to be pointing down, and they're right next door to each other. So carbon 1, carbon 2. You see these dashes, that means pointing down. So let's just call this carbon 1, carbon 2, 3, 4, 5, and 6. Let me just change to red so we can see what I'm going to draw. The axial position at carbon 1 points up. The equatorial position at carbon 1 points down. Chlorine is pointing down. There's a hydrogen in the axial position. Carbon 2, the axial points down. The equatorial points up. So if the methyl group, I put a chlorine there again, didn't I? But this would be methyl if I kept it here. But the second functional group must also point down. So one has to be on the equatorial position. The other will be in the axial position, but they are both pointing down to achieve that. If they were both wedges on that structure, we have a chlorine and a methyl that are both drawn as wedges. That means they are both pointing up. So think that through. Here's my 6-membered ring, my little helpful connected dot. Do your best to make a cyclic structure, and that's not bad. It's not perfect. I'll call this carbon 1. The axial points up, so there's the chlorine in an axial up position. Carbon 2, the methyl also has to point up, but that means the up is the equatorial position, so this methyl group has to be on the equatorial to point up. Takes some practice, doesn't it? And boy, will your model kits really help. This is the skill in your next homework question. Draw both chair conformations for the following molecule. So I have 1, 2, 3. At carbon number 1 is an ethyl. Carbon number 3 is a methyl. I just did that alphabetically. All right, so draw your 6-sided structure. Carbon 1 needs to point up. Carbon 3 needs to point down. That's what the definition here of seeing the dash means pointing up. Seeing the wedge means it's pointing down. Now let's figure out what's happening. Let's call this carbon 1, 2, 3. Carbon 1 will have an axial pointing up and an equatorial pointing down. The ET, that's the ethyl group, must be up. So right now at carbon 1, we have an axial pointing up. This is a hydrogen. Doesn't need to be there, but just remember there is a hydrogen there in the equatorial position. We skip carbon 2, and now we go to carbon 3. Carbon 3, remember this, and I'll just draw that. If this axial is up, this has to be down. If this is down, the next one has to be up. So you can kind of begin to see the equatorial bonds as we begin to draw them. All right, so we're focusing on carbon 3 this time, and it has to be pointing down. The axial is pointing up, therefore the methyl group must be on the equatorial to point down. So on carbon 3, the equatorial bond is being used for the methyl. In carbon 1, the axial bond is being used for the ethyl, and that shows an up-down configuration. Carbon 1 is the ethyl, pointing up. Carbon 2 is the methyl group. And on carbon 2, that's wrong. On carbon 3, the methyl group is down. To draw other possible chairs, we have to make sure that the ethyl group pointed up will be equatorial and the methyl group pointed down will be axial. So that's just really doing a ring flip. From the previous slide, we drew our structure with carbon 1 in axial, carbon 3 in equatorial. So literally take this carbon 1 and push it down. Take carbon 4 and push it up. And when you do so, you're really just kind of showing the opposite parallel lines. So I drew my parallel lines in this direction for the first chair, and to flip it, I draw it in kind of the opposite direction to get the ring flipped. Carbon 1 went straight down. Here's carbon 2, 3, and carbon 4 flipped up. Carbon 1, you still need the ethyl in the up position, so then it went to equatorial. And we still need the methyl at carbon 3 to be down, so it went to the axial position. Equatorials turned to axial, but the position of up and down remained constant. And the other good question here it asks us to consider is, which chair is more stable? And clearly you can see if the equatorial bond contains the larger substituent branch, the ethyl, this would be a more stable conformation, whereas this large flagpole is going to create interactions in what we call the 1,3 diaxial interaction. You would have these hydrogens taking up space and causing steric hindrance with this flagpole position. So this is a less stable conformation because the larger group is up on the flagpole position. Even though we have a methyl and a flagpole here, that group is smaller than the ethyl group, so that's less steric hindrance. Draw both conformations for each of the following compounds. So again, I'm just going to practice another round with you. This is carbon 1, carbon 2, and I'm going to draw the first structure by just leaning my lines to the left. I still like to have those little dots in there to help me connect and create a cyclohexane structure in the chair conformation. I am just in the habit of calling the top right corner carbon 1, 2, and I can just continue around. And remember, carbon 1 then will have a flagpole up, equatorial down. Flagpole down, equatorial up. Flagpole up, equatorial down. See how we're just alternating? Flagpole down, equatorial up. Flagpole up, equatorial down. Flagpole down, equatorial up. You just alternate as you go around the circle. So now on carbon 1 we have a wedge, and I know that wedge means up. Carbon 2 we have a dash, and dash means down. So at carbon 1 I'm going to have a methyl group pointing straight up. So I'll just put a methyl group so you can see that that's where the CH3 is, and the hydrogen, that's the fourth bond, would be in the equatorial position down. Carbon 2, we need the ethyl group to point down, and that means the hydrogen is pointing up. So here we have an axial down. Change the chair conformation, and that just simply means draw your slanted line starting in the opposite direction. Now physically you're taking carbon 1 and pushing it down. You're taking carbon 4 and pushing it up. That's a chair flip. Draw your lines in the opposite direction, leaning the other way, and just connect those little helpful dots to get a cyclic structure. Carbon 1 is now down here. This is now carbon 1. Carbon 1 would have an axial position down, equatorial up. Carbon 2, axial position up, equatorial down. And we just alternate going around the cyclic structure until all the bonds have been shown. Now, at carbon 1, I still need the methyl group to be up. So now it's on the equatorial bond, still pointing up. And at carbon 2, I need the ethyl group to be pointing down. So now that is going to be on the equatorial group. I'll just label that. We went from axial to equatorial in a ring flip. All right. Oh, you want me to do one more? Stick with me if you'd like me to do more homework problems. Here we have a 1,4 interaction. So let's see what we have. I'll get my cyclic structure. There's my cyclohexane. Well, let's call this carbon 1, and there's a methyl group, and it's a wedge, so it's going to be pointing up. And at carbon 4 is another methyl group, so it will also be pointing up. I like to just call that carbon 1, 2, 3, 4. So up, and then the equatorial would be down. Here's my methyl group. This equatorial would be like this, and then like this, and then like this, and so forth. We're just alternating as we go around the ring. So my first is at carbon 1, and I made it an axial pointing up. Carbon 4 needs to have it pointing up, so that ends up to be on an equatorial as the up position. Carbon 1, the axial position is up. Carbon 4, it's the equatorial bond that is in the up position. Do a chair flip. Push carbon 1 down, push carbon 4 up. And just draw your lines in the opposite direction. Ooh, this is going to be narrow. Okay, that is not good. Sometimes I just have to start over. Good enough. All right, so now here's carbon 1 because I pushed it down. And there now is the cyclic structure. So now carbon 1, the axial position is down, the equatorial is up. So that methyl group is now on an equatorial position, but still pointing up. Let's see, so this would be up, this would be down, this would be up. We need the methyl group to be pointing up at carbon 4. It's kind of misleading. It should be more like this. And then this guy will be here, and then this guy like that. And now I have this in the axial position at carbon 4, and at carbon 1, it's the equatorial position. We did a ring flip. We're getting good at this, aren't we? In Cis-trans Stereoisomerism, and again, I said these are stereoisomers because they have their atoms are bonded in the same order, which is different than a constitutional isomer, which bonded in a different order. These are bonded in the same order, but just attached in a different spatial arrangement. For instance, this is known as a Haworth projection, and that was a vocabulary term mentioned earlier. We haven't really done a lot with it, but I said Haworth projections are used for cyclic structures, specifically cyclohexanes, and a lot of sugar molecules and so forth, to just show the stereoisomers for the substituted branches. So let's look at this. This is a carbon 1, 2, 3, 4, 5, 6. That is a 6-carbon cyclic structure. And at carbon 1 and 2, we have substituent groups coming off, methyls. Notice that in the plane of the carbon ring, Both of these methyl groups are on the same side. They are both pointing up. The hydrogens are both pointing down. When we have those substituents on the same side, the conformation is referred to as a cis. And that's the prefix in the name you'll hear. That's called cis 1,2 dimethyl cyclohexane. They're both pointing up. If you're looking at this Haworth projection and you notice that they are on opposite sides of the cyclic ring, opposites of that are known as trans 1,2 dimethyl cyclohexane. Notice this is not accomplished by just twisting the ring. That ring isn't going to twist. You physically had to break this hydrogen and break that methyl bond and actually switch their attachments. So they are not interchangeable by bond rotation. I hear my husband's music in the background. They are not interchangeable by bond rotation. So in other words, they are stereoisomers because they're connected in space differently. So what might that look like in Haworth projections is kind of looking at and seeing if they're up or down. Notice that this is called a Haworth projection. So I'm getting an idea clearly that these are cis because they're on the same side of the bond, right? Both pointing up, whereas trans, they're both pointing down. What does that look like in a chair conformation? Well, if one is pointing up, the other has to point up right next to it. So one would have to be an axial, one would have to be an equatorial bond for a 1,2 disubstituted cyclohexane. If one is an equatorial, the other has to be in an axial for both of those to be pointing up. If it's a trans conformation, they're pointing up and down. See how you have one of each? Here this is up, this is up. That's the same, that's a cis conformation. This one is pointing up, this one is pointing down. That's different. That's a trans conformation. With trans, they could either be both axial or both equatorial. And notice the equatorial would be much more stable instead of having these flagpoles, these interactions between the 1,3 carbons. You're looking at an equatorial tuck around the middle there to keep the steric hindrance low. Cis and trans conformers. Let's try one of these from homework as we approach the end here. Draw a Haworth projection for 1,3 dimethyl cyclohexane. I'm going to stop there and try to draw a Haworth projection, which is really just drawing a 6-sided ring. There's cyclohexane. Kind of give it some stereochemistry. I'm going to kind of darken these lines to let you know that those are kind of coming up out of the page since it's kind of a puckered cyclic structure. So that's my best interpretation of what these were looking like. So I have a 6-sided ring and I just kind of darken these to let you know they're puckered. They're coming up out of the page. So that's my attempt at a Haworth projection. At position 1 and 3, we have methyl groups. Okay, so 1 and 3. Should we call this carbon 1? Doesn't matter, I have to pick a spot. 1, 2, 3. So if this is position 1, here is position 3. Notice I'm just drawing a straight line up and down. To be a cis conformation, I would have both of them pointing up or both pointing down, just so that they're on the same side. This is the cis conformation. And if I wanted to do the same thing for trans, I'm going to redraw my Haworth projection, which is just best I can, drawing a 6-sided ring and then letting you know it's kind of puckered. So these are just like the wedges. I'm just darkening those to let you know those are wedges. This is carbon 1, carbon 2, carbon 3. So a trans would have one up and one down at those positions. There's the trans conformation. Alrighty. So that part's fine. Then it says for each compound, draw the 2 chair conformations. So let's turn these Haworth projections into chairs. So let's start with the cis conformation. I'm just going to try to draw, I'll draw these kind of slanted more this direction. 2 sets of parallel lines. Draw your little helpful dots in the center. And then connect those dots and do your best to form a cyclohexane. That's not terrible. All right, 1, 3. So let's call this carbon 1 and this carbon 3. So if this is an axial, this will be an axial pointing down. This is an axial pointing up. So both of these need to point up in a 1, 3 cis conformation. Or draw your lines slanting the other way. Do your best to draw a cyclohexane. We push carbon 1 down, so now this is carbon 1, 2, 3, and 4 got pushed up. Carbon 1 now has an axial bond pointing down. Carbon 3 now would have an axial bond pointing down. As long as they're in the same position, this is also a cis conformation. They're both pointing up. Oh, you know what? I made them both point down. They have to still point up. I need to erase. So if they both point up, now carbon 1, the equatorial is pointing up. The equatorial is pointing up. So the bond flips, but they still remain up. So up with axial, and on this, they're both up with equatorial. There. I erased all the bad. Let's see. Still cis because they're still both pointing in the same direction. Let's turn our attention to do the same with the trans conformation. There's my cyclohexane. And I'll call this up. There's my first carbon 1, 2, 3. And this now will be pointing down. No. Carbon 2 is down. Carbon 3 axial is up. So the down is an equatorial. Carbon 1 has an axial up. Carbon 3 has an equatorial down. Equatorial down. Now what? Do a ring flip, which just means to me is draw your parallel lines the opposite direction. There's my helpful dots to connect. This sometimes mostly works, and that's good enough. And then now carbon 1 got flipped down, so here it is. Carbon 1 now is this type of look. 2, so this would be up, this would be down. So now we need the methyl group to still point up, but now it's going to be on an equatorial doing so. And carbon 3, we need this to be pointing down, so this is axial. Ooh, that was good work. We just did a lot of stuff. We drew 2 Haworth projections to show you cis and trans conformations, and then turned each of those 2 Haworths into their own separate chair conformations for cis and trans. You feel like a little artist, right? The last little section I'm going to allow you to just read through and take your own personal notes, reading a little bit about polycyclic systems. That's up for you to read. You can see that that was my last slide. The section is rather short, so just kind of go through and read a little bit about interesting polycyclic systems that's of interest to you. And my friends, I think we did it. The end. One day closer to done. Oops, that was just me thinking out loud.